Hey, seventh grade. So our learning target today is I can find experimental probabilities. You should be on page 1. So let's start by talking what is experimental probability. Well, experimental probability actually comes from the word, the definition comes really from the word. It's the probability or the chance based on an experiment. Like what happened, based on what happened, what the experiment, what the results of the experiment, what's my chances? So kind of sounds crazy because the definition is within itself, but it's a probability based on repeated trials of an experiment. So flipping coins. Well, what happened? What were the results? We can calculate our probability from the results. That's experimental probability. So we're going to go ahead and take a look at the formula. For the formula, we say that the P, the probability of, that capital P stands for probability of a certain event. So you would have to put the name of the event in here. For example, you could talk about getting heads. If you're getting heads as you're flipping coins, what's the probability that you get heads? You put the event's name in that spot. What's the probability of getting red when you're drawing marbles? You put the event's name. You put the number of times the event occurs on top. So you just look at the results. Pretty simple. Look at the results. How many times did I get heads? Put that number on the top. And then in the denominator, we always put the total. And that's how we calculate the probability. Now we can turn that into a decimal and a percent, but really we just start in fraction form. So here's example 1. In example 1, it says that 13 out of your 20 emails in your inbox are junk emails. So typical, right, of email. So only 7 of the emails that you get are actually valuable. So 13 out of 20. So in the way we would write the notation, what's the experimental probability that they are junk? We would say capital P, probability of the event's name would be junk. What's the probability that we get junk? Well, we just look at our results. It would be in fraction form. 13 junk out of 20 total is our experimental probability. Now in my class, I'd like you to turn that into a percent. So you can go ahead and divide 13 divided by 20, multiply by 100, and you would end up getting 65%. So 65% of your emails would be junk emails. So that would be the probability in fraction form, and I prefer that you always go straight to percent. Another way to get that percent if you don't like the fraction decimal relationship is just go back to the idea of we know cross products and that percent is out of 100. It's kind of a lot more work, but some of you are real comfortable with that. All right, so we're going to go ahead and move on here in example 2. In example 2, part A, it says it rains 2 out of the last 12 days in March. What's the probability that it rains in March? So based on the experiment, what's the probability of rain? That's the event's name. So we would say, how many times did it rain? Well, it'd be 2 out of how many total times? 12. How many times did it rain? 2 out of how many total times? 12. There's our fraction, 2 out of 12 based on the experiment. And we would need to turn that into a percent. We could go cross products on it or just divide, multiply by 100. And I'm going to have us round just to a whole percent right now, which would be 17%. You could also have 16.6666, 16.67% would work, but just for simplicity reasons, I'm going to call that 17% chance that we get rain based on the experiment. So now, part B is what we call experimental probability, like a prediction of. So we take the experiment, we use our results to make a prediction of what happens. And some of you are going to love this because it really turns into a T-table cross products. So we're talking about how many rain days we have out of total. So we said it rained 2 out of 12 days. There's our fraction. Here's your T-table. How many days would you expect it to rain in the month of April? Looking at the calendar over here, April has 30 days in it. So we're saying, well, how many days would you expect it to rain out of 30? Cross products solve. T-table, good old stuff that you're so good at. Go ahead and T-table this, cross products solve. Start with the variable x, multiply the diagonal. X times 12, multiply the other diagonal. Hand method kicks in. All of you should know how to solve that. So we get 12x equals 60. You end up with x equals 5 days. We would expect in the month of April, based on our experimental probability, that it's going to rain 5 days. Okay, guys, let's keep on rolling here. In example 1, we talked about junk mail. We talked about that the probability of junk mail based on the experiment is 13 out of 20. So now we're going to say, what is the probability that is not junk? So if we have 13 junk emails, what's the chance that it's not junk? So first of all, we should start with saying, well, if we have 20 junk emails, pardon me, if we have 20 total emails and 13 are junk, then the remainder emails, the emails that are left over would be, we would say 7, and they would be considered not junk emails. So our notation then here would be, what's the probability of not junk? That's the event we're talking. The not junk emails is the event. And we would go ahead and write that as a fraction and say, we know 7 not junk out of 20. So that's our fraction, and we're going to want to go ahead and turn that into a percent. Now we can go t-table cross products on that. We can go fraction decimal, whichever your preference is, but we're going to go ahead and want to turn that into a percent. So 7 divided by 20, multiply by 100, or a t-table. Either way, you'll find out it's 35% of your emails are not junk. Now, a couple things to talk about. Some of you might be like, yo, Ms. Volkman, here's the gig. You told us up here that it's, or we calculated up here that 65% of my emails are junk. So if 65% of my emails are junk, then it has to be true that 35% of my emails are not junk. I get that. So if that is your mindset, I'm totally cool with that. You did not set up that t-table. You did not set up that fraction. You just subtracted from 100%. If you saw that, fabulous. Give yourself a star there. Super. Let's move on to you try number 2. Okay, you try number 2 is a great example in real life. So at a clothing company, an inspector finds 5 defective pairs in a shipment of 200 pairs of jeans. Now, the reason why some companies like TJ Maxx are in business is because there sometimes is defective pairs that come into the shipment. So let's go ahead and talk about what we have here. We have the probability of the event's name is that we're going to get a defective pair of jeans in the shipment. So I'm going to go ahead and write probability event's name defective. Total goes in the bottom. We have 200 total jeans in the shipment, and 5 are defective. We have 5 defective out of 200 total. So if I read the question, it's asking, about how many would you expect to be defective in a shipment of 5,000 pairs? So we're asking to make a prediction based on our experiment. So how many would we expect to be defective instead of out of 200 if the shipment were out of 5,000? Go ahead and take t-table cross products. Go ahead and solve that. Start with the variable x. Everybody should be grabbing that calculator at this time. Multiply that diagonal. So that's 200 times x. And multiply that other diagonal. 5 times 5,000 is 25,000. Hand method kicks in here. We divide by 200, copy, paste. So we should come up with an answer of 25,000 divided by 200. We end up with 125 pairs of defective jeans. 125 pairs of defective jeans. Okay. So that's experimental probability and making predictions. The good news is we go back to some of our skills that you're really good at. Cross products, hand method, all those things. All right, so let's take a look at example 2. Here's our last problem for today, guys. Hang in there. So we have this experiment where we're just taking a dice, which they call a number cube. Just know that they're the same thing. A dice is a number cube, and we're going to roll it 50 times. We're going to do this experiment. We're going to just pick it up. We're going to roll it. And in the table, you can see the results of the experiment. If we follow the bar graph up, it looks like we rolled a 10. Pardon me, we rolled a 1 10 times. We rolled a 2 4 times. Followed up, we rolled a 3. It looks like 8 times. We rolled a 4, looking like 11 times. And we rolled a 5, looking like 8 times. We rolled a 6, 9 times. Very important that we write those numbers on the end of the bar so we don't have to reread that information. Total of 50 rolls. What is the theoretical probability of rolling an odd number? So in theory, what's the chance I get an odd number? So we would say, what's the probability that I get odd? In theory. So how many are odd? Well, the numbers 1, 3, and 5 are odd. So we have 3 odd chances out of 6. So the chance that I get an odd is actually 50%. I have a 50% chance in theory to get an odd number when I roll a dice one time. So let's go ahead and see if that's what we got for our results. So in our experiment, now let's find the experimental probability. It looks like we rolled, so again, we're talking probability of odd. We rolled 50 times. Now, how many times did we get odd? So we have 10, 8, and 8. So we got a 1, a 3, and a 5. We add those up. 10 plus 8 plus 8 means that we rolled an odd 26 times out of 50. Go ahead and type that in. 26 divided by 50 multiplied by 100 means that you rolled an odd 52% of the time. So was it perfect? No. Was it close? Yes. We said that we had a 50% chance of rolling an odd, and we got a 52% chance in our experiment. Pretty darn close, acceptable answer for sure. Okay, so let's take a look at this next example. Last example of the day here. Whoops, sorry about that. What is the experimental probability of rolling a number greater than 1? What's the experimental probability of rolling a number greater than 1? So we're really talking about what's the probability of getting 2, a 3, a 4, 5, or 6. Well, there are 6 ways that that can happen, and I have a 2, a 3, 4, 5, and 6. 5 out of 6 chance that I will roll a number that big. So 5 out of 6, if I would type that in my calculator, 5 divided by 6 multiplied by 100, or set up a proportion, is an 83% chance that I'm going to roll a number greater than 1. 2, 3, 4, 5, 6. Let's see if in the experiment that actually happened. So we're really talking about this chunk right here. If I were to add those up, how many times did I get a 2, 3, 4, 5, and 6? When I add those up, that occurred 4 plus 8 plus 11 plus 8 plus 9, which is really 40 times out of 50. I got a number greater than 1. That's an 80%. So divide and multiply by 100 is 80%. So I had an 83% chance that I was going to get that in theory, but when I did the experiment, I got an 80% chance. Again, pretty darn close. Not perfect, but a pretty darn close match of what I thought would happen. Your learning target today was, can you calculate an experimental probability? So an experimental probability is really just using the results of an experiment. We do turn everything in my class into a percent, so make sure that you're turning it all into percents. Your homework for tonight is to finish page 2, page 3, and page 4. So finish page 2, all of page 3, all of page 4. I'm looking for percent answers in tonight's work. Have a fabulous night.